Thank you for coming to my talk, and today we're going to talk about Linux kernel keystore and why you should use it in your next application. First, a big round of thank you. I know it's been a hard day and you're all tired, but you still find the strength to come to my presentation, and we'll have some bash code and interesting stuff in the presentation today, so hope you will enjoy it. Yeah, before we begin, actually, how many of you actually know that the Linux has a keystore? Oh, some people. Some people. Nice. Okay, so a little bit about myself. My name is Ignat. I do Linux at Cloudflare. I'm passionate about system security and performance, and I enjoy low-level programming. Linux kernel bootloaders, IoT devices, drivers, and other low-level scary C stuff. Since recently, I'm actually a fugitive programmer because US NSA banned corporations developing in C and C++, and that's the only thing I do. So yeah. So let's get to why it happened, why NSA banned me, and why do we need to think about application keys and memory. So it's not a joke, actually. NSA put a recommendation out there recently that it kind of like encourages to develop software in memory-safe languages, and this is because of a study they made that 70% of all the vulnerabilities in software for big corporations like Google and Microsoft came from various memory access violations, right? So let's see how it plays out for application keys or cryptographic material or secrets or whatever. To understand this, we need to review the concept of the operating system address space. Who here doesn't know what an operating system address or process address space is? Oh, cool. So it will be quite fast, right? So we have many processes in our operating systems because we run a multi-process operating system, and each process has an address space, so a dedicated chunk of memory where everything is related to the process is stored. But what it is exactly stored in the process address space? So first, it's main logic, right? So your business logic, your application logic, it resides in the process address space. If your code uses some kind of shared libraries, they also reside in your process address space. Then you have the data for your program, so it can be intermediary computations, customer data, whatever, some temporary data which passes through your application. And we also have either one stack or several stacks, right? So if your process is multi-threaded, each thread has a stack. And also, your processes don't run in vacuum, so they run on kind of like an operating system like Linux, and you have the kernel space address space. And unlike the process address space is kind of flat, it's not separated between the different parts of the kernel. And again, in the kernel, we have the kernel code. We also have some static and dynamic data for the kernel. We also have some drivers, right? If you use loadable kernel modules, they are loaded directly into the kernel address space, which can be some scary thing. And again, you have the stacks for the kernel threads, right? And the idea of the process address space that anything within the address space can access anything, like main logic, but mostly it's main logic and libraries can access any data or anything on the stack within the process address space, and the same thing happens in kernel. The kernel space is completely flat, and this is why like loadable kernel modules are really scary, because once you load the module, it can actually access kernel core code, any static and dynamic data, whatever, or any stack of any other subsystem. But one process cannot access the address space of another process directly, right? And also, none of the processes can access the kernel address space. So this is what's called the typical address space isolation of the operating system, right? But why it is important? So let's zoom in a little bit into the process, and let's actually zoom in. What could we store in its data section? Not a section, it's kind of It may be several sections, but what kind of data can be there, right? So it can be like internal state, like you write your code, you store some data structures, temporary computations, and they're stored in the operating system, in the process address space. It can be user or customer data. If your process processes some customer data, it can be temporarily stored in the process address space. And the most scary part is cryptographic keys, right? So if you run an HTTP server which does TLS, you have cryptographic keys in your process address space. And the best thing about it, if your code or a library you somehow becomes compromised because of the process address spaces, all your data is compromised, right? All three of that. But we can say that we just determined that not all data is created equal, right? So what if your application internal state is compromised? Well, is it bad? Well, it depends, right? It depends on what your application does, how your code has been compromised. For example, if your internal state is compromised in a way that can change the expected application flow, it can actually lead to further compromise, but sometimes not. So it depends, right? Well, what if user or customer data gets compromised? Who here didn't hear about Equifax? Oh, encourage you to read that, because Equifax has a massive data breach, and a lot of its customer data has been compromised, and it's very bad, right? There are severe consequences. They had many court hearings. They paid expensive fines, and they're still paying out to some folks for their data. It's bad, right? But it's not the end of the world. Like, it's very hard to recover from it, but still possible. But what if a cryptographic key gets compromised? So this is a game over, because your data integrity is compromised, your full security may be compromised, and your identity might be taken over. And we saw a massive example in the who here remembers Heartbleed. So when a lot of server cryptographic keys were leaked, and so we had to rotate the whole internet to actually not allow some malicious entities to impersonate websites on the internet, right? So given this, like, we should be paying more attention to protecting cryptographic keys, right? So how data may be compromised, cryptographic keys specifically? Well, there are some typical types of vulnerabilities, categories of vulnerabilities, which lead to that. First, it can be compromised through untrusted inputs and out-of-bounds memory access. So you have a piece of code, and you have temporarily data, which is your just application data stuff in your memory, but the way because process address space is kind of flat, you may have a cryptographic key written next to it in your memory, right? And usually the expectation from your code that it would only access the stuff, but if you somehow misprogram your application, and it can be directed to read past the expected stuff buffer, so it can read and dump the cryptographic key. And this is what exactly happened during the Heartbleed attack, that OpenSSL didn't properly validate untrusted input, and therefore cryptographic keys, it was possible to dump cryptographic keys through the network, right? Secondly, your code may be vulnerable to arbitrary remote code execution, and actually there is nothing to discuss there. So, like, if somebody can direct your application to do something else, they can always direct your application to read the cryptographic key from memory and dump it, whatever, right? So easy. And this is what exactly happened in Log4Shell. So one of the examples is Log4Shell, but there are many others, right? Your keys may leak due to some buffer reuse. For example, in this simple example, we have a process stack, and here's your main code, which occupies some part of the stack. Now, imagine this is some kind of like an HTTP server which decrypts data with TLS. So at some point, it may call some kind of decrypt function, and that decrypt function will get a cryptographic key from somewhere and store it on the stack. Yeah, and once the function finishes decrypting data, it just terminates, but it may leave the key on the stack, and the next function we call, for example, logging function, can accidentally access that material and dump it to a log, right? This is why, basically, if anyone here did some kind of like security compliance, you always meet this requirement that we should always zero the cryptographic material before our code terminates, right? So we should always zero the memory where cryptographic keys were stored. And this example shows the buffer used on the stack, but similar thing can happen on the heap. But actually, it turns out that satisfying this requirement is quite hard, especially in garbage-collected languages like Java or Go, because you don't actually have control in which memory your cryptographic key may be stored. And it's not only security vulnerabilities which can accidentally leak your cryptographic keys. Simple bugs can as well. So imagine your application crashes, and your system may create a thing called a core dump, which is the exact snapshot of process address space at the time of crash. And that snapshot can contain cryptographic keys as well. And if somebody gets access there, they can get your keys. Inappropriate logging, debugging, all these things can leak your application data as well as cryptographic keys, right? So what should we do about this, actually? Well, some may say, let's not have the memory violation vulnerabilities. They're just bugs, let's fix them. And we know, and like it's not possible to fix all the bugs, otherwise we'll not be sitting here and continuously discussing like all the things like about vulnerabilities, right? So it's not possible to fix all the bugs, and therefore it's not possible to fully protect ourselves from memory access violation and application data leaks, right? But because cryptographic keys are so much more important than the rest of the data, can we do something specifically for cryptographic keys? Can we protect them better? And it turns out we can. So imagine what we can redesign our software, right? So we have our main process. What if we spawn another process, right? And it will have its own data section, and we will move the cryptographic keys from our main process to another process with its data section, right? Then we would probably need to write some additional code, which we'll call a crypto logic. And this code will create like a well-defined interface between the two applications, where the main application will allow you to somehow use the cryptographic key stored in the process address space of the another application. And this model is quite common these days, so I call it an agent model. So we have two processes, a main process and a helper agent. And the main process doesn't have direct access to the cryptographic material, and it's ensured by the underlying operating system via address space isolation. And main kind of communicates with agents through a well-defined, stripped-down, easy-to-audit interface to perform cryptographic operations on its behalf. And the way how it works, so main process usually processes untrusted input and usually is network-facing. The agent, on the other hand, doesn't process untrusted input, so only requests with this well-defined interface and is usually not network-facing. So there are some, think of the agent as a software security key, like a YubiKey implemented in software, and we see a lot of examples out there. So who here uses SSH agent? Who doesn't use SSH agent? Hope nobody doesn't use this. Yeah, we have the GPG agent as well, so many agents. But there are drawbacks to this model, right? So now, instead of one application, we need to develop two applications and processes. We also need to design this well-defined interface. Is it really well-defined? Is it the minimal that we require? Can it be like violated by untrusted input or something? We also need to somehow add communication support between the two processes, like Unix socket, shared memory, whatever inter-process communications we have. And probably we also need to somehow authenticate the main process in the agent process, because now that we have this agent process, how can we ensure that only main process can talk to it to perform cryptographic operation and not any malicious process on the system, right? So it's more work. This is where we come to Linux kernel key retention service, or a simple term, you can call it just a Linux key store. And the concept is quite simple, actually. So we go back to our agent model, but instead, what we do is we replace the agent process with the Linux kernel. And we already have the well-defined interface in place called system calls. So this is exactly what Linux kernel key retention service does. It stores your cryptographic keys or secrets as kernel objects. It was actually initially designed to share cryptographic material with the kernel for in-kernel services. For example, you send the key to do the Linux disk, because Linux disk encryption implemented inside the kernel, you need to somehow provide a key, decryption key to the kernel to actually do that operation. So it was designed for encrypt or encryptFS, but it was later extended for user space program to manage their keys. And the advantages is similar to a typical agent model, that keys are stored outside of the process address space, and there is a well-defined system call interface to access and use the keys. And now, because keys are now kernel objects, they, like other kernel objects, they have associated access control bits, and they also are subject to security check inside the Linux kernels, like you can write LSM policies like SEL Linux, or use some other LSM modules to actually really fine-grain access to the key. And one of the most powerful things, that key lifecycle can also be implicitly bound to the code lifecycle. As I will show a little bit later, we can solve this auto-destruction of the key when your code terminates, even if your code was written in a garbage-collected language, because it will be enforced by the operating system. And surprisingly, for a kernel feature, it has good documentation. So you can also read that. So let's dive into the key store, how it works, right? So to talk about key store, we need to understand some terminology. So key store has key rings and keys. So key rings can contain other key rings, or key rings can contain keys. So it's kind of like you can have this key hierarchy or key structure, which is very similar to a file system on your machine, but specifically for keys. So keys, they are actually objects that contain actual cryptographic material. They can be read, written to, or used to perform cryptographic operations. There can be different types, which we'll dive in shortly. They can user, logon, asymmetric, encrypted, and trusted. And they're very similar to a file in a file system, but the difference is that a key can be included in more than one key ring, apart from the file included in only one directory. So a key can be present in several key rings at a time. Key rings are like a collection of keys. They contain so-called links to keys and other key rings, and they kind of enforce this life cycle of a key. So as I mentioned, the key can be linked to several key rings, but a key cannot not be linked to a single key ring. As soon as the last link to the key is destroyed, the key gets garbage collected and securely wiped from the RAM by the kernel. Key rings can be explicitly created or special, which types like thread, process, user, and session. I will dive into them a little bit later. They do, as I said, they enforce key lifetime, and they're similar to a directory and a file system. So let's see an example. By the way, this is like a slide, but when it's in this black box, it was copy-pasted from a real terminal, so consider it as a demo. And when you get this presentation, you can actually copy the commands and run them yourself, right? So in this example, we are creating a new keyring and link it to my user keyring. I will explain what and user is a special type of keyring which is implicitly created by the system for my user. I will dive into a little bit later, but as far as like now, we just created a custom keyring, linking it to my keyring, and then I can create a key of a user key with the contents cryptographic material hunter2 and add it to my keyring, right? And then I can display my current key hierarchy. So you can see we have these two are special keyrings. This is my session keyring, this is my user keyring, this is my custom keyring, which I just created, and my custom key, right? And yeah, you can see that each key or keyring is designated via a small integer. It's called a serial number. And I can also now read my key back. Like, so the key is now stored in the kernel. I can ask the kernel, give me the key material, and I should have access to that because it's my key, so I can read the key material back. So yeah, Hunter2. Another example, which you can use a kernel keystore to actually share cryptographic material between users. So imagine we have two users on the system, and you may notice that these users don't have any common things, or they're not part of the same group or anything. Two completely different users on a single system. So let's imagine the first user creates a new key in their keyring, in their user keyring called Hunter2. Now the second user may create a new keyring under their user keyring. And what the second user can do, the second user can allow other users to write into that keyring, but not read from it. So it can set permission. The keyring name is from others to actually receive secrets from other users. And then once that's done, the first user can actually move their key from their keyring to that to the Bob's keyring. And we can now see that Alice doesn't have access to the key anymore, so because it was moved to the Bob keyring, and Bob actually, now having access to the key, can actually read the cryptographic material, and it has the key in their key hierarchy. So it's just a simple key sharing mechanism between users. So now we see custom keyrings and we see implicit keyrings. So implicit keyrings are very powerful. They can be of three types. So they can be process keyrings. Implicit means you don't have to explicitly create them. The kernel will create these keyrings for you, and they're always accessible. And their life cycle is bound to whatever the kernel object is creating them, right? So we have process keyring, so we have the session keyring, which is accessible to the current process and all its child processes. We have a process keyring, which is private to a specific process, and we have a thread keyring, which is private to a thread, which is very powerful as well. So imagine if you design an HTTP server where it serves several domains at once, and each domain have their own TLS key, and you design it in a way that a domain is served per thread. So each thread may store the TLS key in the thread keyring, and we can guarantee that other threads can never access that key, even if they run as part of the same process. We also have user keyring, so their lifetime is bound to user objects. So we saw in the example the user keyring, it's shared between all the processes with a specified UID. There is another special type of user session keyrings, which is very similar to user keyring, and the difference are not important for this presentation. There is also a type called persistent keyrings, and they're not persistent because they have a backing store, so none of the keys are backed to disk or whatever, but they just have a different lifetime. So persistent keyrings were designed not to be automatically destroyed when a bound object is destroyed, but, for example, to have a timeout before destruction. So they're mostly useful for non-interactive tasks or cron jobs, which create a random user to run the task and then destroy the user afterwards. But you can still store the key material for that job in the persistent keyring, so it has access to that key between the runs. Let's see how what the power of keys and keyring lifetime, implicit lifetimes in real-world examples. So in this example, I will create a new key in my session keyring. So Hunter2 adding to my session keyring, like at S means the session keyring. And yeah, and I can display my key hierarchy. I have my session keyring, and under that I have my secret, right? Yeah, and we can verify that IDs are the same. Now in in another terminal, in another window, I will run a BPF trace program and put a hook on a kernel user destroy function, which is responsible for securely destroying a key. And if in the first terminal I exit my session, I log out from the system, I would immediately see that the kernel will destroy the key, because the session keyring is bound to my current process, my SSH session, and when I exit, the process terminates, the session keyring terminates, and because the user key was linked only to my session keyring, it also gets terminated securely. And I can verify that I can re-log in back into the system, and I will see that I don't have access to user secret anymore. And we can also see that the session keyring ID is different, because on my next login, the system created me a different session keyring. So these are powerful because selecting the appropriate keyring type, you can ensure the keys will be securely destroyed when not needed. If you're writing like server applications, probably the typical keyrings you would use would be process or thread keyrings, because even if your process crashes for whatever bugs, you are guaranteed that the kernel will securely delete all the keys associated with the process, and from its memory. Clear so far? So now we talked about keyring types. Let's talk about key types. So in the example so far, we used only one key type called a user key. And it's the most simple type of key. It's just a kernel object which stores cryptographic material. So imagine we have a user key, so a process has some cryptographic material. It can create a user key in the kernel. And another process can read the key if they're allowed to do so and get the cryptographic material. Easy, like an in-kernel buffer. Right? We have logon keys. So logon keys are very similar to user keys. They're just buffers pointing to cryptographic material. But the difference is, so a process may put a key as a logon key inside the kernel, but you can never read the key back. And it was mostly designed for in-kernel cryptographic services like LUKS, Encrypt, or encryptFS. So for example, if you're running a very recent Linux distribution and you have full disk encryption enabled, and I hope everyone does, if you check your full disk encryption setup, you will notice that the keys are actually stored as a logon keys inside the kernel for your disk encryption. So you can never read them back, you can never get back so the keys are stored there when initially the crypt setup utility runs, but when it terminates, you can never read the disk encryption key back from the kernel. One of the powerful key type inside the Linux kernel key store are asymmetric keys. So imagine you have an RSA key. So what you can do is you can store that key inside Linux key store, and other processes may not have to read the key, but they can do cryptographic operations on top of that key. So they can decrypt or sign the data with the private key, never having to have access sorry, to the actual cryptographic material, which is very powerful for things like HTTP servers or like SSH agent, for example. So in this example, we're kind of mimicking how would a typical SSH agent replacement would work with the Linux kernel key store. So here we generate a random RSA key. The only thing we need to convert it to so we need to convert it to PKCS8 format, because this is how the kernel understands the private key, asymmetric keys, and then we can actually add that key as an asymmetric key to our session keyring, for example, to ensure, like, let's say it's the same way like an SSH agent works, right? So you add a key to an SSH agent, and and the session keyring is very useful here, because once we log out, our in-kernel private key would be automatically destroyed, right? And then we can actually sign some data with the key handle. So we can sign ABC, and later we can basically verify that whatever signature we produce, it would work. We wrote a really extensive blog post on this, and I encourage you to read it. I will provide links at the end as well. So the blog post deeply explores the asymmetric key type, and we actually also provide a working patch for OpenSSH to replace an SSH agent with Linux kernel keystore. So in the future, you don't have to run SSH agent, so you can just add the key to the Linux kernel keystore, and OpenSSH will just pick it out automatically to authenticate you to the servers. Clear so far? So up until this point, we were talking about, like simple users of Linux keystore. How can your application utilize it? But let's talk about how we can put it on an enterprise level, right? And the big question for key management systems is how can we, like in all the previous examples to provision the keys, our application still had to touch the cryptographic material. Some process on the system had to take the cryptographic material and put it inside the kernel. So therefore, we have this moment where the key material is exposed to user space, and therefore any vulnerability potential vulnerability can dump it from there, right? So how can we actually provision these keys directly into the kernel memory without user space ever needing to touch a single byte of cryptographic material? For that, there are interesting new key types. One interesting key is called encrypted key. So imagine we have a setup where the kernel already has some kind of key provisioned inside, right? We'll call it a wrapping key. So what a process can do, a process can take a wrapped key, so an encrypted key, and put it inside the kernel specifying the wrapping key, and the kernel will automatically unwrap the key. So in this case, inside the kernel, the key material is plain text, but in the user space, the key material is always encrypted. So user space doesn't touch the cryptographic material in this case. And when somebody tries to read the key back, the kernel will automatically wrap it again. So the processes can read the keys, back it up, but they will never see the actual cryptographic materials. But this approach has a chicken and egg problem, so how do you get the wrapping keys in, right? There is a different type of keys which tries to solve that, where we replace a wrap key with a TPM. And this becomes much simpler. So with TPM, you have a wrapped key with a TPM. When you try to insert it in the kernel will use the TPM to securely unwrap your key. And when you try to read it back, it will be wrapped by the TPM again. But going back and forth to TPM for each key is quite expensive because TPMs are quite slow. And like in our case, they actually break at scale, to be honest. A trusted platform module, a security chip which is present on most laptops, modern laptops and servers. And if it's not present, you can actually buy them for several dollars or pounds. So in this case, it's very convenient to use some kind of combined schema, right? So let's say you have a process which needs a key, you have a TPM and a kernel, and you have some kind of special provisioner process, and then you have some kind of either cloud or on-premise KMS or HSM system which stores the root key for everyone, right? So now you can provision this root key through the TPM, so you can wrap it to the server's TPM, send to the provisioner process on your system, and the provisioner process will put the key inside the Linux kernel, which will be automatically unwrapped. So now the kernel has access to the root key. And then a specific process, and that can happen only once on boot, for example. And then when a process needs a key, it requests the wrapped key from our cloud or on-premise HSM, and then it puts into the kernel, and it gets unwrapped with the root key. So this is software operation, so it's much faster. We don't exercise TPM that much. So far, so good. We kind of solved this problem, but we have some problems, right? Yes, we solved that the application never sees the plain text of cryptographic material in the process address space. But there are still the schema is inconvenient because applications are still responsible for contacting the centralized HSM or KMS system to get their wrapped keys. And what it means, they need to know how to reach that system, right? So they need to somehow store the URI endpoints in each application configuration. You have to explicitly program the code to interact with the KMS or HSM communication protocol. And there is also a little administrative control of the created key objects, right? So let's say if application gets a wrapped key, puts it inside the kernel, but sets on it invalid permission or like loose permissions, then some other process may actually try to read the cryptographic material or use the key, right? And again, then KMS or HSM subsystem needs to somehow authenticate each requesting process because we don't even want to provide wrapped keys to arbitrary processes or arbitrary requests. So how many of you used Vault in your, yeah? So sounds familiar? Vault is a great system, but you need to interact with Vault, and like in our case, every application needs to somehow interact with Vault and have code for or supporting scripts to interact with Vault. But Linux kernel can help with that. So there are actually two system calls which you can use to provision the key. So far, we've been using a system call called addKey, which is basically adds a key to the specified keyring with the provided payload. So application takes payload, encrypted or not, uses a system call to actually store or unwrap the key inside the kernel. And the payload is interpreted according to the key type. So plain text payload is taken for user or logon keys, private or public key is taken for asymmetric keys, and wrapped key is taken for encrypted and trusted keys. But there is another system call called request key, and it's a little bit different. Applications does not provide payload anymore. Application just requests the key from the kernel. It's like a platform feature. So give me my key, and that's it. And naturally, every system is different, and your kernel probably doesn't know where to give the key, where to get the key from, but you can help the kernel. So you can have a special helper program which will kernel hook into to actually satisfy these requests. So, and this kernel, this helper program can hook into your external KMS system, and it also, this helper program can enforce properly key permissions on instantiated keys. So it's kind of like it's a more centralized and transparent API to add keys to the keyring. So the way how it would work, let's say an application may, if a process needs a key, what it basically does, the only thing it needs to know is what is the key identifier. And key identifiers can be arbitrary strings inside the Linux kernel keystore function. So you can have like some random key identifiers assigned to applications. They can either be derived or the application can store them in their configuration file, but they're just identifiers. There are no URIs. They don't have to have awareness of any KMS or HSM system you use. So the process can just issue a request to the Linux kernel, give me my key, like cloud app key 1, and the kernel will create a placeholder inside the kernel address space for that key, but with no cryptographic material. Then the kernel will spawn a special helper program called sbin request key, which is part of like modern Linux distributions, but that program is modular, so you can write your own modules to it in any programming language, and you can configure this helper program to actually, based on the key ID, to actually direct this program to various key sources. So for example, you can have like key store in HSM in the cloud and some test keys. And depending on like which key was asked, like if an application asked a key from like with a cloud prefix, it can direct it to your cloud KMS HSM systems. So then the cloud KMS HSM system provides a response, basically with the requested wrapped key, back to this helper program, and that helper program satisfies the request and instantiates the key for the application, and then the application can actually use that key. Clear so far? Yeah, so request key is a single centralized operating system API to request key for all applications. And the advantage of it, there are no KMS HSM connection string for each application, no URIs, and just a free-form string ID. And this approach actually decouples your application code from your KMS system, right? The only thing that application needs to know about is its key identifier, and it should be able to do request key operation, interact with the Linux kernel. And it's a more secure way to instantiate keys in the kernel. So the kernel is designed in a way that once it calls this helper program to instantiate the keys, only that helper program have access to actually complete that request. So you cannot have a malicious other process which will like dump some garbage into instantiated keys. The callout process, I call it a callout process, can perform additional security checks. This is what we do in our production environment. When we get a key request, we can actually verify some attributes of the process, like what executable started that process, what is your user ID, group ID, process ID. So we can technically implement arbitrary ICLs and policies for key access. We can also support multiple storage backends. So, for example, we can, depending on the key ID, we can direct some requests to our production KMS system, some IDs to the test KMS system, some IDs we can just generate a random key and provide it to application. And application, the logic of this is fully decoupled from the application itself. And now we have only one process which needs to be authenticated in the cloud KMS system. So only this process, so cloud KMS doesn't have to authenticate every request, so it needs only to authenticate requests coming from these authorized processes on the system. And yeah, as I mentioned, these backend connectors can be written in any language. So the request key binary is written in C, but you can actually write modules in Python, Go, Java, whatever. So by utilizing request key, the key management and distribution, it becomes a core service of the operating system itself, as it should be, even in enterprise scenarios, and you can, like support arbitrary KMS and HSM setups with it. Whew. This is basically all what I wanted to say for today. So here are some links. Most of them are links to kernel documentation and man pages for all the features I just mentioned. So I still encourage you to go and read our blog post about the kernel key service. So it has a full working example how to patch an OpenSSH server to use Linux kernel keyring instead of an SSH agent. It also has some fun code which illustrates how you can accidentally leak a cryptographic key with a buffer use scenario. So all examples are copy-pastable, compilable, and ready to use. Thank you very much, and I'm ready for questions. Yes, please. I will put that back.
You mentioned that you all had some trouble with TPMs scale. Could you talk, if you can, could you talk? Oh, sorry, repeat it. You mentioned earlier that your company had some issues with running TPMs at scale. If you can, could you share like what was breaking?
I mean, it's general, I think, hardware reliability of a specific server configuration. So one of our generations, when you try some thing with the TPM and now you're ready to deploy it to production. Let's say I want to read TPM ID from every server at Cloudflare, and when I launch it, I can see that a non-zero percentage of the fleet does not respond to the command, and TPM becomes unreachable until you reboot a server. Some TPMs even like stop working at all, and then when we open the server, we see the burned chips there. So basically, I'm not sure, like, this is a lesson for us as well. So like when we now procure hardware, we try to incorporate some resilience testing for such things. So sometimes they're not very well tested on the factory. Yes?
Should the Linux key store be used in containerized environments? And are those cases, in that case, different from what you showed here?
This is a very good question. So unlike many other features of the Linux kernel, the key store subsystem is not fully namespaced. So I think it only namespace for user namespaces. So there are some quirks around that. So there are some still possible attacks where, for example, if you manipulate your own key store inside the container, you can actually manipulate something outside on the host system. And this is why in modern container setups like Kubernetes or even Docker, the keyring syscalls are usually blocked by seccomp for now. But we're working on it.
So I guess for example, managed, like fully managed Kubernetes, like Cloud Run would be even
well, I guess
harder to.
the way how I approach it, it's a blessing and a curse, right? So on the other hand, if I manage my own Kubernetes cluster, right, I don't want the KMS code to run in the container. I want it to be the feature of Kubernetes itself. So Kubernetes can be that hook. So this has to execute on the host. So for example, if a container in some namespace requests a key, my host system replies and supplies that key, as it should, like with any other Kubernetes subsystem. I guess you can, if you use LSM hooks, basically, you can design a proper secure solution for that, but it has to be very well tested that you can, the containers cannot somehow manipulate the keys outside of their jurisdiction, I think what you mean. Yes?
Is there a way to generate a key in the key store as well?
Yes. So at least for trusted and encrypted keys, there is also a way you can add the key with 0 bytes, and in this case, the kernel will generate one for you internally and provide you the wrapped version. So yes, technically, you can have a setup where you generate a random key, get the wrapped version, and then provide the wrapped version, which will be unwrapped, and then the user space will never see the cryptographic material associated with that key. Yes? Just a moment.
Yeah, this is just something basic, but what's the point of the wrapped key?
What's the point of the wrapped key?
Yeah, if I have the wrapped key in a process, I cannot use it because it's encrypted, right? So why would I use it?
The thing is, Linux kernel itself doesn't provide any mechanisms of key persistence, right? So every key object inside the kernel is in memory. So you lose all your keys when you reboot. So for example, but you may have your own setup where you extract the wrapped key from the kernel and back it up somewhere. And then when you have to use it again, you take it from the backup, put it back in the kernel, and can unwrap it. Also, I guess the key secret sharing example could be extended by using a wrapped key. So for example, I can just create a wrapped key and give access to some other application, use it, but never read the cryptographic material, but I can still share that key with that application. Any question more? Going once? Go, yes?
So, as I understood, there is a system call to get the key, which the process can use.
Yes.
Is there any protection if we do this buffer overflow and we inject syscalls in the stack? I know where to ask for the keys. Is there any protection?
Well, you mean, sorry, I quite don't understand. So
I mean, if we have a vulnerability in the application, and with the buffer overflow, I can inject the assembly code and do the system call.
But
so I could ask, I'm still in the same user space, so I can ask the kernel to do something with the keys or give me the key.
But you can only, keys are represented in user space with their serials ID, which is kind of similar to a file descriptor. So you can only do it's a well-defined interface in the way that you can only perform operations on these objects you're entitled to. So if you're not allowed to read the key, you can't do that with the key serial. So eventually the kernel will validate what kind of permissions do you have for that key. And if you don't have the permissions to read the key material, it will not allow you the system call.
Yeah, because as understood, I mean, we use the keystore to protect the keys that, for example, if I'm HTTP server, I have some key which I need for decrypt, I store it under my user space. But then if there's malicious, if vulnerability with the buffer overflow, I can actually inject the code which asks the kernel to give me the key.
Well, you can store.
I already stored.
Yeah, I got the question now. So what you can do is, for example, you can store the key inside the key store, like an asymmetric key, and then prohibit yourself to actually read the cryptographic material, only to use the key. Yes, you would still be able to inject some code which will ask your program to use that key to sign something with it, but it will never be able to read the key material back. So because it will not be allowed anymore.
Okay. But if the process is allowed, they can ask for the key.
Yes.
I don't know the API of this.
Yes. If you have a read permission on a file, you can read a file. It's similar to a key. You had it? Or similar?
Yes. So a continuation of your answer or parts of it. So you can use a functionality in Linux called seccomp BPF to restrict the system calls that are allowed in the process, so that after you've done your initial key stuff, you can say that after this point in time, this process is not allowed to do certain system calls, and in that way you can, if you're compromised after that, then it tries to do one of these sensitive system calls, then your policy that you installed can cause the program to crash, for example, or not do anything or something like that.
Yeah, good call regarding seccomp. Also, what we use, we recently adopted the BPF LSM system. So instead of writing a policy for each application, you can have a system policy written in BPF, and you can attach to key hooks and you can write a BPF script which kind of have your specific logic of who can access what, so you can veto it or do whatever.
Is it in any way related with if you use a desktop Linux system, there is also a program called keyring? Is it in any way related, or does it use this system under the hood?
I don't know, to be honest. You mean the keyring in the
like a GNOME keychain application?
The GNOME desktop, is it?
Yeah, for example. Yeah.
I think GNOME desktop uses this functionality for logon keys or something like that. Like many modern Linux things use this, but I'm less aware about how desktop uses this. I mostly know that disk encryption uses it, and we're kind of use it a lot.
Yeah, okay. Thank you.
So I guess the big move here is, instead of saying, okay, we're going to have unencrypted keys in our at runtime in our code, the idea is to move those keys into the kernel so that like you mentioned Vault earlier. Vault has that sort of offloading the encryption to Vault. So here you're offloading the encryption to the kernel. So is that something that's scalable and can be used in production as an ongoing thing? So we can say, look, there's no circumstance in which you should have unencrypted keys in user space. It should always be only at the kernel level, and you should be doing all your encryption, decryption through the kernel. Is that something that's scalable?
Good question. So I recently discovered that the actual RSA code inside the kernel is not that great. It's very slow, and it didn't even use, like, if you know crypto, Chinese remainder theorem. But we're actually like, I fixed that. It's upstream now, and like, if you have, it depends on the architecture, and like if you have a really fast and secure crypto code inside the kernel, yes, it's scalable. But kernel, the upstream kernel code needs a little bit of work and improvement, but hopefully it will get better as the adoption increases. Yes?
So how do you securely authenticate and authorize the callout program? Towards your cloud HSM, for instance?
So it's up to you how you design that. So we specifically were using the TPM itself and trusted boot and secure boot, like all the combination of it. So we kind of boot the system in a trusted state. This program is like more important. So for example, you can hook into, if you know Linux IMA, integrity measurement architecture, that it wasn't, like, for example, modified or compromised in any way, and then you can use TPM attestation to prove that to the cloud HSM that all these events happened, and then you can proceed. But you only need now one program instead of you have to do it for the whole system. Any more? Going one? Oh, yeah, okay. Still have time, no worries.
When it comes to asymmetric keys, are there other algorithms supported than RSA?
No, but I've been relentlessly trying to submit a patch for ECDSA, but I get ignored. But the patches are there, so you can download it, and it was well tested and works. It's just somehow the maintainer for that specific part of the code is busy with something, and they keep not responding to my emails, but the patches are there. I think, yeah, ECDSA should work soon, and yeah, other crypto code is also. Like Linux crypto API is kind of very extensible, so if you have some C skills, you can write your own crypto driver implementing arbitrary algorithm, as long as you know how to do that.
Right.
Well, we have a crypto driver which uses boring SSL inside the kernel. I have to write a blog post about it. It's also a very interesting story. If any more questions, like, catch me outside. Thank you.